Bismillahirrahmanirrahim. Assalamu alaikum. We were discussing quantitative methods of forecasting, and the third method that we will discuss is exponential smoothing. Exponential smoothing is more sophisticated version of weighted moving average that we discussed in the previous segment. It requires minimal data to forecast demand for the next period. It requires forecast for the current period, actual demand for the current period, and a weighting factor or smoothing constant designated as alpha. This method successively assigns lower weights to the older observations. So that is common with weighted moving average. But the value of the weights decreases exponentially in exponential weighted moving average where the value of weights decreased linearly. This method is useful if the recent changes in the data are significant and as a whole, this method also does not directly address seasonality or linear trend. Especially to address linear trend, we have to adjust this method. Using this method, the forecast for the next period t plus 1 is equal to smoothing constant into actual demand of previous period t, plus 1 minus alpha into forecast of previous period, the period t. So if we further explore this formula, so this becomes alpha into a subscript t plus 1 minus alpha. Now this f subscript t is actually equal to alpha into a t minus 1 plus 1 minus alpha ft minus 1. And similarly, if we further explore this term ft minus 1, so it will have a subscript t minus 2, and if we move further, that will be having a t minus 3. So the point is, we are reducing the weights and we are assigning that weight, the remaining weight other than alpha to all the previous periods. So that is, for example, if we have alpha is equal to 0.3, so we are assigning 30% weight to the actual demand of the previous period, that is the most recent period, and the rest of 0.7 is assigned to the actual demand of all previous periods. So period A subscript T minus 1, period A subscript T minus 2, and so on. So you can further explore this formula to see that eventually you are going to have exponential weights assigned to all periods other than the most recent period. So that is why it is called exponential smoothing. So as we saw in the previous slide that we need three pieces of information: the smoothing constant, alpha, actual demand of most recent period, and forecast of most recent. So A subscript T is actual demand for the present period, F subscript T is the previously determined forecast for the present period, and alpha is the weighting factor, that is smoothing constant. And we will see that determining the value of this alpha is very critical. So that is the question. What should be the value of alpha? Should it be, for example, a smaller value or the larger value? And one point that was not mentioned here, that alpha is greater than or equal to 0 and less than or equal to 1. So that is the range for alpha. So should it be closer to 0 or should it be closer to 1? So is there a way to decide this value of alpha? So we will see this point in some detail. So if we are having the random variations in the data, and you could see that this is the same data that we discussed to explain the effect of the value of n, the number of periods in the moving average method. So you can see that there are random variations in data, significant changes in the data from period to period. So if we have a relatively larger value of alpha, say zero point 0.5, so you can see that the forecast, these dots, they very well respond to the changes in demand. So you can observe from here. And if we keep on decreasing alpha, say if the alpha is 0.3, you can see that the forecast, this line, does not very well respond to the changes in demand. So that responsiveness was better in the case of larger alpha. And if you further reduce alpha to say 0.1, so you can see that uh, there is even less responsiveness to the changes in demand. So the forecasts respond to the changes in demand very less as compared to larger alpha. So in other words, we can say that smaller is the alpha, say 0.1, there is more smoothing, the forecasts are closer to each other, but the forecast does not respond effectively to the changes in demand. And at the other extreme, when the alpha is large, there is the forecast responds very well to the changes in demand, and there is less smoothing. So if there are random variations in the demand, that is generally the case, then we use larger alpha. And if the data as a whole is stable, there are very little or minor variations from period to period, then we can use a relatively small alpha. So that is the a key takeaway. So we will solve an example using the same data as we have been seeing, and we will see the impact of so we are having the same 2 years data as we discussed previously. And in the first case, we are taking alpha to be equal to 0.1, and we will forecast um, for the 2 years, including the January 2020. But the question is, if you remember the formula for simple exponential smoothing, that requires the most recent forecast as well. So we, for example, want to forecast for February. So we do need the forecast for January, but we don't have that. So there are different ways that we can use. We can use qualitative method of forecasting. We can use a simple moving average to forecast for the first period, to set a benchmark forecast value to start with, to set a baseline actually to start with. So in this case, we are going to use the naive forecasting. So the forecast for February will be equal to actual demand of January. So that we have a baseline forecast. Using exponential smoothing, the forecast for February will be equal to alpha, that is 0.1, into actual demand for this month, for the previous month, that is February in this case, plus 1 minus alpha into forecast of the previous month, that is February. So that was 437 found using naive forecasting. So the forecast for March is equal to alpha into actual demand for February plus 1 minus alpha into forecast for February. And we are going to fix the cells for alpha in both cases. This cell C3 is fixed here as well as at this point. So now we can drag to forecast for all the months, including the month that we require to forecast right now, that is January 2020. So we will compare these statistics once we use the larger alpha, but you can see that here again we are under forecasting. So you are having tracking the positive and having very large values. So there is a lot of bias in this forecast. So again, for February, we will be using the naive forecasting method. And here we are going to use alpha into actual demand for February plus 1 minus alpha into forecast for February, and alpha is 0.5. Drag to find the forecast for the rest of the months. And once again, you can see here the tracking signal is having positive values, and there is bias in the forecast, and as a whole we are under forecasting. So forecast as a whole is less than the actual demand. So if you produce according to the forecast, we will be facing stock outs or back orders. So you can look into this to adjust your forecasts, because forecasting is the part of planning. So you can beforehand make appropriate decisions to avoid back orders or stock outs. And now we will compare the results using alpha 0.1 and alpha 0.5. So you can see that for alpha 0.1, the forecast is not responding to the changes in demand. So this is the curve for the demand. So there is more smoothing. The forecast values are closer to each other, but they are not responding to the changes in demand. But for a larger alpha, 0.5 in this case, the forecast is very well responding to the changes in demand. And of course, the smoothing is less. So the forecast error for smaller alpha is larger as compared to forecast error for larger alpha. And same you can see for MSE, mean squared error, is larger in this case for alpha 0.1 and smaller for alpha 0.5. And similarly, MAPE is larger for alpha 0.1 and smaller for alpha 0.5. So that is the point. If there are random variations in the data, you should use larger alpha and vice versa. And the standard deviation is small for smaller alpha and large for larger alpha. That is showing the smoothing. But we don't need smoothing actually. We need the forecast to be more responsive to the changes in demand. If our data is showing very little variations, it is more stable, then we can move to smaller alpha. So once again, we focus on the same point. So if alpha is 0, so our formula will turn out to be, that was our formula. Forecast for next period is alpha into actual demand of recent period plus 1 minus alpha into forecast for the recent period. So for alpha 0, this term will become 0. So we will have forecast for the next period equal to forecast for the previous period. So we are giving no weight to the actual demand of the recent period. So that is the point. Now, if we go to the other extreme and if we set alpha is equal to 1, then this term will become 0. So we will have forecast for the next period equal to actual demand for the previous period. So that is actually forecast is based only on most recent demand. So it is the same as the naive forecast. So we have to, of course, remain in between, and we have to see, we will see um, in one of the following slides. Actually, we'll use Excel to set the optimum value of alpha. So the higher alpha is, the more sensitive the forecast will be to the changes in the recent demand. So this is what we saw. The greater the alpha, we are giving more weight to the most recent demand. And the smoothing will be less. The closer the alpha is to 0, the greater will be the smoothing effect, as we saw in the case of alpha 0.1. So the most commonly used values of alpha are in the range of 0.1 to 0.5. So now we will see how we can set the optimum value for alpha using Excel. So we have the same Excel sheet where we applied the exponential smoothing method using alpha 0.5. But these values of alpha 0.1 and 0.5 were decided arbitrarily. So now we will see how we can find the optimum value using the solver function in Excel. So first we set the objective function. So in this case, like in the case of weighted moving average, we are going to set mean squared error cell to be the target cell. And we want to minimize mean squared error. So we will select min by changing variable cells. So cell containing alpha is our decision variable cell. And what would be the constraints? So one constraint is that this alpha should be it should be greater than or equal to 0. And this alpha should be less than or equal to 1. And that's it. So if we solve, we get the optimum value of alpha to be 0.69, 0.70 if you round off. So using this value of alpha, we will get the minimum error. So for any value other than this value, we will get the higher error. So you can play up with these values and change. Say, if for example, we have MAD of 191. So if we have 1, this value 252 for alpha 0.50, this will be 192. So the minimum value we get is using alpha 0.70. For all other values, this error will be larger than this minimum value. Finally, an important conclusion, that is the larger value for n, that is the number of time periods in moving average, has the same effect on a forecast as a small value of alpha in exponential smoothing. So that is an important conclusion. So we can use this simple formula actually to see this impact. So for example, if n is equal to 1, so alpha will be equal to 1 as well. So you can see that n is actually the smallest value for moving average that we can largest. So for n is equal to 2, alpha becomes 2 divided by 3, so that is about 0.66. For n is equal to 3, alpha becomes 0.50. So as we keep on increasing the number of periods in moving average, the alpha keeps on decreasing. So for n is equal to 4, alpha will be equal to 0.40. For n is equal to 5, alpha will be 0.33 and so on. So the effect of greater periods in simple moving average is the same as the effect of smaller alpha in simple exponential smoothing. So greater are the periods in simple moving average, there will be greater smoothing, but the forecast will be less responsive to the changes in demand. And same is true for small alpha. There will be greater smoothing, but less responsiveness to the changes in demand. And the opposite is true for small n and larger alpha. So this was simple exponential smoothing. Thank you.